Hello everyone, my name is Ali Mohammadi and today we will be learning about Hess's law. So what is Hess's law? Hess's law states that the enthalpy or the heat change that accompanies a chemical reaction is path independent and only depends upon its final states and its initial states, in other words, its reactants and its products, given to you by that equation below. Delta H of the reaction equals the sum of the delta H of the products minus the sum of the delta H of the reactants. And it's important to note that this is at constant temperature and pressure. So here we have a typical Hess's law problem that you'll see in tests. And we start out with our first purple target equation. It's called a target equation usually by most lecturers, including Dr. Rogers in Chem 1441. And we have some unknown delta H. The question being, calculate the enthalpy of the reaction above. You are also given, depending on the type of question, in this case we have three black given equations with all specific delta H values. In this case, they're all negative, indicating they're exothermic reactions. And it's always important to note that delta H is measured in kilojoules. And I know this might seem daunting, but we're going to actually take each equation, we're going to call them equations 1, 2, and 3, and we're going to take it step by step to solve this problem. So like I said, this can seem daunting, so we're going to take this step by step. We take our first given equation, 6MnO solid plus O2 gas yields 2 moles of Mn3O4 solid with delta H of negative 464 kilojoules. It's always important to remember that delta H is measured in kilojoules. And we see that we've got a compound, Mn3O4 solid, that is in common in both the target purple equation as well as our given red equation. So we want it to look exactly like the target equation. Remember, I said you have to always focus on your target equation. So step 1, we want to switch it over to the reactant side. We switched Mn3O4 solid onto the reactant side. And anytime we switch a reaction around, whether you're switching to the reactant side or the product side, you always have to change the sign of your delta H. So in this case, we go from negative to positive 464 kilojoules. Step 2, we got to make sure the number of moles are the same. You always want to make sure the number of moles are the same as the target purple equation. So we are going to multiply everything by 2. You've got 2 moles of Mn3O4 in your given. You want 4, hence you're going to multiply everything by 2. And that's everything in the reaction, not just Mn3O4. So you end up with 4 Mn3O4 solid yields 12 moles of MnO solid plus 2 moles of O2 gas with a delta H of positive 928 kilojoules. That is equation 1. So just like we did with an equation 1, we have our given equation 2, and we find that Mn2O3 solid now is what is in common with the target purple equation. So just like we did with equation 1, we have to switch the reaction around. This time we're going to the product side, and we change our sign of our delta H from negative 142 to positive 142. Step 2, just like we did in equation 1, we've got to make sure the number of moles are the same. This time we have 6 moles of Mn2O3 in the target purple equation. So we got to multiply everything by 3 to get the number of moles of Mn2O3 the same. So we multiply our entire reaction by 3 and we get our final reaction at the end with a delta H of positive 426 kilojoules. So if you look here, we've lined up all 3 of our manipulated equations, and we accounted for Mn3O4 in equation 1, MnO2 in equation 2. And the oxygen gas was actually affected. We have 2 moles of O2 gas in equation 1, 3 moles in equation 2, and that adds up to 5 moles of O2 gas on the product side. But in equation 3, we actually have to multiply everything by 12, which gives us 6 moles of O2 gas in equation 3, and you'll see later on that by canceling out, we'll get the 1 mole of O2 gas that's found in the purple target equation. So I know what I explained on the last slide was a bit complicated, but when you line up all 3 reactions and add them up together, it really becomes simple. So we lined up all our equations 1, 2, and 3, and we see that a lot of things can actually cancel out. Because whenever you have something that's the same on the product side as well as the reactant side, you can cancel them out. So we've got equations 1, 2, and 3. You can see that 12MnO solid from equation 1 and 12MnO solid from equation 3 cancel out. They're on opposite sides, and they're exactly the same. Equations 2 and 3, we've got 12MnO2 solid being the same. Those cancel out. And we've got those 5 moles of oxygen gas on the product side in equations 1 and 2, and the 6 moles of oxygen gas in equation 3 that I mentioned. If you cross those out, you get 6 minus 5, which gives you that 1 mole of O2 gas in the target equation. You end up with your 4 moles of Mn3O4 as well as your 6 moles of Mn2O3, which in the end turns out to be your final target equation. You add up all your delta H's, keep in mind the signs, and you end up with your final answer of negative 278 kilojoules. So here we've done one example problem. Yay, we're on to example problem 2. Now, this is what I would like to call one of the tricky but non-tricky problems. It's typically going to ask you something like this. Calculate the heat of formation of MnO2. Now, you're probably freaking out because there's no target equation given. What do you solve for? Well, don't fret. You've been given 2 equations in black, which are your given equations, and you actually form the target equation, believe it or not. I'm going to show you how to do that. So to create our target equation, we use what we call heat of formation, which is forming a compound from its standard state elements. So in our case with MnO2, we use manganese solid plus O2 gas. Both of those elements would be in their standard state in those forms to form 1 mole, remember only 1 mole of the compound. To find delta H of formation, you'll notice the sub F, and that's how we get our target equation. So now that we have our target equation in purple, we would use our 2 given equations, manipulate them just like we would in example problem 1, and solve for our final 2 equations. I know you see fractions in these 2 final equations, but don't worry, they will eventually cancel out when we put them all into perspective. So if we line up both of our 2 given equations that we manipulated, you'll see that those fractions actually do cancel out due to being the same both on the products and the reactants side when we add up the reactions. Similarly, we'll get our purple target equation down below when adding up the reactions, and our final delta H at negative 520 kilojoules. Hey guys, thanks to all of you who watched this video. I really hoped it helped. I know you guys are gearing up for finals right now, and I hope this is just one of the extra tools that will help you get that A.